Welcome to second semester of physical science. Welcome to our new students and welcome back to our old students. For Unit 6 Part 1, we're going to explore the very beginning of energy and really go in depth with work. Energy is the ability to cause change or to do work. So when I say change, for example, taking this water bottle and moving it around, I'm changing its position. That requires energy to do. Any kind of change. For example, the lights are on in the room. Now they're off. Now they're back on. That was a change. It was light, then it was dark, then it was dark, then it was light. That requires energy. Any kind of change requires energy. It's doing work. You have probably no idea who these guys are. There used to be a show on MTV like back in 2006 through maybe 2010 called Robin Big. I really loved the show growing up. I shouldn't say growing up. Back when I was beginning to teach. But they always had a catchphrase all the time. They would say, "Do work, son, do work." So anytime I ever got to the units, energy and work, I always incorporated them. But again, energy is the ability to do work. The units for energy and work are the joule. Now, it is important to understand that work and energy are synonymous. They basically mean the same thing. Work is energy, and energy is work. Later in another video, we'll explore ideas like kinetic potential energy, but again, this one's focusing just on work. So what is work? What's it mean to do work on something? Well, work is a transfer of energy over a particular displacement due to a force. I'll repeat that. It's a transfer of energy, the amount of energy to use a force on an object over a particular displacement. And it's found using the following equation. Work equals force times displacement times cosine theta, where theta is the angle between the displacement and the force. You may get a little confused with this cosine theta, but again, this video should hopefully help you all out. If we put it in formula terms, it would say W equals F triangle X cosine theta. And I hate, for those of you who are new, you'll learn that I hate when people just say the letters. Do never say the letters in the equation. Say what they mean. You can write the letters. Don't write the words, because that takes forever to do. Write the letters, but say the words. So I would say work equals force times displacement times cosine theta. Remember, this is the symbol for displacement. It's the change in position of something. This was covered back in motion. This is unit 4 for us. Not sure if you came from Mr. Wilson, what unit that was in. Let's do an example kind of looking at this. It says, how much work does a weightlifter use to lift 1,600 Newton barbell, which is the weight of the barbell, over his head 2 meters? Well, again, what's the equation? The equation for work is force times displacement cosine theta. The force, which in this case is the weight of the barbell, is 1,600 newtons. What's the displacement? How far did he move the barbell from the starting location to the ending location? He moved it 2 meters. Technically, someone may argue, doesn't displacement have a direction? Okay, upward. I should have said 2 meters upward. I did say over his head, but I'm talking about right here. And then the angle is cosine 0 degrees. Now you're probably going, how did he get cosine 0? I will explain that very shortly. It is imperative, however, you memorize 3 very important angles that involve cosine. When cosine is of 0 degrees, whenever you take 0 degrees and cosine of that, you always get 1. So cosine of 0 degrees, that's how it's worded correctly, cosine of 0 degrees is always 1. Remember that, remember that, remember that. Cosine of 0 degrees is 1. The cosine of 90 degrees is 0. Again, cosine 90 degrees is 0. And then cosine of 180 degrees is negative 1. Negative 1. Please get these 3 cosine angles memorized. So I did 1,600 newtons times 2 meters times cosine 0, which is 1. So essentially I did 1,600 newtons times 2 meters, and I got 3,200 joules. That would be the amount of work this weightlifter did to lift the barbell 2 meters above his head. Now, let's go ahead and look at ways I can figure out more about this cosine theta and more questions involving work. Is Chloe doing work on the book? Ask yourself the following question. What is the equation for work? Work equals force times displacement times cosine theta. Is Chloe exerting a force? Clearly she is. She's pushing up on the textbook. So Chloe is exerting a force. So then the question is, what is the book's displacement? Meaning, what is the straight line distance from just the beginning point to just the ending point in direction? Well, considering the book's not going up or down, the displacement of the book would be 0. Therefore, think of the following. If your force is F, your displacement is 0, and there's a cosine theta, well, what's force times 0 times cosine theta? Anything times 0 is 0. So right now, Chloe is not doing any work on the textbook at all. However, let's say Chloe now decides to lift the book above her head. So as she's moving the book upward, there is a force acting on the book by Chloe's hand, so she is pushing upward with a force. Notice there's also a displacement as she lifts the book. The displacement points in the same direction as the force. So then the question becomes, all right, what is the angle between up and up? Well, the angle between up and up is the same angle between down and down. It's the same angle between left and left and right and right. The angle between two vectors that go the same direction is 0. So now to figure this out, Chloe is doing force, so if we know her force, we can take that number, times displacement, times cosine of 0. What is the cosine of 0? As shown in an earlier video, the cosine of 0 is 1. And you have to just memorize this. The cosine of 0 is 1. So Chloe is basically doing her force, if we knew that number, times displacement times 1. It's important to know that Chloe is doing positive work. When the force and displacement point in the same direction, you are doing positive work. Now, let's pretend, well, not really pretend, but now let's say Chloe is going to lower the book. What kind of work is she doing, if at all? Well, she still has a force acting on the book. She's still pushing up on the book. So she's not pushing down, she's actually pushing up on the book. She's just lowering it. So the displacement is down. Next question is, what is the angle between up and down? It is the same angle between left and right. The angle between opposite vectors is 180 degrees. What's cosine of 180 degrees? Cosine of 180 degrees is -1. So if we wanted to calculate the amount of work Chloe was doing on the book as it lowered downward, we would do the force of her applied force pushing up on the book times the displacement as she lowered it times cosine 180 degrees or just -1. So you see that her work is actually negative because we multiply it by -1. So very important to understand this. When force and displacement are in opposite directions, you have negative work. I repeat that. When force and displacement are opposite directions, you have negative work. When they were in the same direction, you had positive work. Well, now let's pretend, what if force goes one direction and displacement goes perpendicular to that? So Chloe's going to hold the book but walk to the left. So again, she's still exerting a force upward on the book, represented by the yellow arrow, and she's moving to the left, a displacement represented by the red arrow. Well, what's the angle between up and to the left? It's the same angle between up and to the right. Same angle between down and to the left and down to the right. It's 90 degrees. What is the equation for, it's not equation, but what is the value of cosine of 90 degrees? Again, a number you gotta memorize, it's 0. Cosine 90 degrees is 0. So what's her work? All right, well, work is force times displacement times cosine theta. So cosine 90 is 0, so it would be force times displacement times 0. Anything times 0 is 0. So again, Chloe is not doing any work on that textbook as she moves it to the left. She may say she's doing work on the textbook because her arm got really tired, but realistically and mathematically, she did no work as she held that book in her hand and moved to the left. Now let's look at a situation where we actually try to solve something quantitatively. Kirsten is pulling a wooden block. As you can see here, there's a red arrow. She's going to be pulling it to the right. So that'll be the displacement. Her force is also to the right. She's moving the block at a constant velocity, which is very important. Both the block and her force point to the right. Since both vectors point in the same direction, what is the angle between them? Good. Hopefully you should say 0. Since the angle between the force and the displacement is 0, they're going the same direction, is Kirsten using positive or negative work? She would be using positive work. That is correct. So again, the amount of force she's using to pull that block is 2 newtons. And again, it's moving at a constant velocity. So let me ask you this. If you are moving at a constant velocity, what kind of forces are acting on the block? Balanced or unbalanced? The correct answer is balanced. Because you're moving at a constant velocity, you have to have balanced forces acting on you. Okay, well, if Kirsten's pulling with 2 newtons of force, what's another force acting on this block? Besides the weight of the block and besides the normal force. Good. Hopefully you said friction, which is represented by the green arrow. So there's friction acting on this block. Now think of it like this. If you're pulling with 2 newtons of force and your forces are balanced, what has to be the force of friction? Well, it's also 2 newtons. It's just pointing in the opposite direction, but it's also 2 newtons because the forces are balanced. Next question is, what is the amount of work actually done by each person, and then not really each person, but by Kirsten and then by friction? Well, let's say this. As you can see, the block moved roughly 0.98 meters. That was the displacement. The displacement of the block was 0.98 meters. The amount of force used by Kirsten was 2 newtons. So, what is the work done by Kirsten, who moved the block with 2 newtons of force, 0.98 meters, and she pulled it in the same direction as displacement? What would her work be? Good. Hopefully you got a positive answer. Next, what is the amount of work done by friction? Now, friction acted on the block the entire time Kirsten was pulling it. So again, the amount of friction we said was 2 newtons. The block moved 0.98 meters. However, the friction pointed in one direction and the displacement was pointing in the other direction. So what is the angle between opposite angles? Not opposite angle, but opposite directions. So good. Hopefully you calculated work and you got the same numerical answer. However, it should be negative since, again, force goes one direction and then displacement goes the opposite direction.